a lot for inviting me. It's really an honor to be here. I can't overstate how good it is to be an intro. This is Jacob Ziehout. He's a PhD student, a very talented PhD student at Columbia. And this is a project where we're going to write down a novel dynamic mechanism design problem, which we're going to try to make as disgustingly simple as we can in order to study the interaction between particular design elements. So I'm going to have a model where there's going to be a principal. The principal's problem is going to be to select a project. We're only going to want to select one project, so the question is which project should they select? To select this project, they're going to enlist the help of an agent. And this agent is going to be an expert at assessing the quality of any given project. However, the agent is going to be biased towards selection in that they are not going to care about the quality, but they're going to just want to have anything selected. The principal is going to care about quality, and so they're going to have to figure out how to incentivize the agent to reveal their information. Okay?
The agent wants any selection, or does he want it to be fast, or
as soon as possible? Yes. Fast.
So there's no option of no selection, or is
there? There is not.
Okay.
Okay, so the question we're going to be interested.
What does the agent do for the principal?
They will see what the project's quality is, and they can tell something about that to the principal.
They're going to rate the project.
Right. So, before I kind of get into the details here, let me just tell you about the kind of situations that we have in mind. So our leading application that I want you to think about is the problem that a company might face, or a board of directors of a company might face, when it decides that it wants to be acquired. Okay, this is a problem that's very common, as we found. And typically when this happens, it's up to the CEO to make a proposal to the board about what kind of which options there are and who this acquirer should be. Okay, now there's various reasons that have been proposed about why CEOs might have expertise in assessing the quality of any potential acquirer. Let me maybe not get into all of those reasons why, but regardless of how it happens, what the CEO does is, given some potential acquirer, they have the ability to approach the board with a particular proposal. Okay, now what's going to be very important for me to talk about is that I want to think about the case where these possible acquirers might emerge over time. Okay, so they might make this decision that they want to be acquired. Okay, but it might actually take some time for a good acquirer to come. So the conflict here is that the board is going to have an interest in maximizing shareholder value. So they're going to want to have a company that is going to be very good for advancing the interests of shareholders. The CEO is going to want just to have an acquisition be made. Okay, now there's various reasons why each of those, that's kind of the natural incentive conflict to study in this situation. In the United States, there's this idea known as the Revlon Doctrine, which basically forces boards in these situations to act in the interest of maximizing shareholder value. And CEOs, on the other hand, their terms might specify some kind of buyout options or some golden parachutes, which are kind of we're there to kind of attract the CEO in the first place, right? But can't be adjusted very easily, once you actually get to the situation of wanting to be acquired. Now, what can the board do? So the board has two different options. So the first is obviously they can approve this decision or not. Okay, but they also can scrutinize any decision, any kind of proposal from that the CEO makes, and I want to talk about that because that's going to be really. I just want to highlight that because this kind of idea that they have can undertake due care activities is going to be really central to what we talk about. Okay, so I think this example broadly resembles the kind of problem I was talking about. The key feature here is the ability to resample following a rejection. Okay, the idea that if you don't like this given acquirer, you can always find another acquirer. You can always ask for it, try again. And I think that's kind of our leading application, but I think these are reasonably general problems, and we think our model applies to lots of situations. So we'll model this bias in a pretty reduced form way, and kind of start with the simplest, most minimal model, and I can kind of tell you what would happen if we modify it in various ways. Okay, So, problem, how should the principal select a project? Assuming kind of access to any arbitrary mechanism. A class, and obviously the answer will depend on what tools we assume are at the designer's disposal, okay? So a classical answer might be to, pay the agent in some way. However, in practice, particularly in these kinds of board-CEO relationships, the possibility of transfer is at least appears to be second order. They often these kind of within firm contracting typically doesn't feature flexible transfers as we might assume. And there's many various stories you might tell about why transfers could be second order in this particular application. What we are going to think about is the possibility of performing costly verification. So this is following a fairly recent literature on the use of costly verification without transfers, which was largely inspired by this paper by Ben Poor and Thappa. The idea here is that the principal is going to be able to pay some fixed cost. And if they pay that cost, they will see what project quality is. Okay? So you could think about this as just the principal exerting effort. They're kind of scrutinizing this proposal that's being made. You could think about it as, in order to figure out the quality of the acquirer, I need to hire some third party to audit this report. Whatever story you want to tell, we're going to model this as some fixed cost, that when the principal pays it, they learn what the project quality is. Okay? And in terms of this application, we like to think about this as an example of good care, because in the law and economics literature, people talk a lot about it. Okay, so we know everything about this. Tell you what we don't know, but I think we know a lot. And to describe the optimal mechanism, it's going to basically, there's going to be two different parts, two different cases that I want to separate. So the first is the case of the low verification cost, when the verification cost is not too large. I'll tell you exactly what that is more formally. Okay, but the idea, so what we're going to show is that in the case of low verification costs, the optimal mechanism will be characterized by a deadline, at which point the principal will select a project irrespective of quality. Before the deadline, the agent is going to be able to make a proposal to the board, okay, or to this principal. And given a proposal, the principal will verify with intermediate probability. And our main result is that that probability is going to be declining over time. Okay, so the idea is that, and we call this a property decreasing skepticism. So the idea is that the principal of the optimal mechanism will verify agent claims of quality with intermediate probability, and that probability will be decreasing over time.
So there's a chance that I don't verify, and there's a chance that I do. But if I don't verify, just say yes.
Yeah, that will be, if the agent makes a proposal, that will be what happens, yeah.
There is only one project?
There's only one selection.
But the agent says, I want to select one or several projects?
Yeah, the agent, on path, the agent will make one proposal. So the agent will only one time say, accept this project.
But when you say verification, it means that when the agent says this is the best project, then you verify this is the best project, not the quality of the project, but it's comparison.
So we're going to take quality to be binary in the model, so if it's the best, then it means it's good. And so we can talk about what happened about that assumption, but
what is the cost of line of telling that into?
agent is not going to have any. I'll have the model on the next slide, but agent will not pay the cost of that.
What is optimality here? In what space of mechanisms is that?
Yeah, I'll write down the objectives formally. We allow arbitrary, since we're assuming commitment, we allow for arbitrary mechanisms.
Mechanisms that involve verification, the possibility of verification is the only tool that you allow them.
Well, as we'll see, the ability to kind of make a selection rule is also a tool, right? So we allow for kind of arbitrary approval decisions. We'll see that the role of that a little bit. But our focus is on, this is a paper about verification. So our focus is on the use of verification.
Is it clear that saying no without verification is pointless? just give me the next
That
one.
it's not obvious, it's also not true. So, we'll talk about that. In fact, that's kind of the second part. So, in the case of high verification costs, the solution is almost the same, except that there's an initial phase where the principal does not utilize this verification device, but rather they will, if the agent makes a proposal, the principal will randomize the approval decision. Okay, so that's the sense in which it's not entirely true. So so in the high verification cost case, the optimal mechanisms are almost the same, except you have to augment the mechanism with an initial screening by a randomization phase.
Are the verification costs externals? So when they are low, this is the optimal mechanism. When they are high, this is the optimal mechanism. This is what the first and second part say.
That's it. So it's,
Can you give us some idea about what low and high mean?
yeah, I will later. So I want to say that there's another paper that kind of mentioned that identified the possible need to do this screening. We're not taking credit for that. What we are taking credit for is the observation that this verification phase is backloaded. Okay, that you always will do this. The use of verification is always the second thing that happens, and it always happens at the end of the mechanism. So that's kind of what I want. I'll give intuition for everything, but I just want to be clear about that. Okay. So I'll get to the model. I think hopefully everything will become clear there. I think a lot of the intuition for what goes on, I think, comes in this T equals 2 case. I really like two-period models where you can kind of just make everything very simple and easy. Then I'll kind of go through our general approach, tell you about our general result, and kind of conclude with whatever I have. Okay, so time is going to be discrete. It goes from 0 until capital T. We take T equals infinity for the main model. In the talk, I'm going to illustrate the ideas of the T equals 2 case. We have some interesting things to say about the finite horizon case, but I don't want to focus on that. I think the main focus is on the infinite horizon case. So there's going to be a project quality or type, which is going to be denoted by theta. It can either be high or low. This is going to be private information of the agent. And the project quality is going to be IID across periods. Okay, so the probability that a given project is high quality and any period is Q. So with probability Q, the project is high quality, with probability 1 minus Q is low quality. Okay. If you'd like, you can think about Q being kind of small, so it might actually take some time for high quality to come.
As I understood before, you said only one project. Now you say every period is a different project.
A different project, only one selection can be made, but it might take time.
Just to be sure. Okay.
Yeah, that's right. You could also think of it as there's some default project, and you're waiting for you're waiting for a new project. That's kind of an equivalent interpretation. So once there's an allocation, the game ends. That's it. And this verification device, it works as follows. So in every round, the principal can pay a cost C. They pay this cost, they learn the project quality perfectly, and the agent pays no cost to provide the information. So no communication cost, just cost of learning what the project quality is. Okay? Clear? Okay, so if the principal ends up selecting a project with quality type theta, then the principal's payoff will be theta. The agent has a value of selection, which is just 1. So the agent gets payoff of 1 if a selection occurs.
Discounted?
There's discounting. So there's a common discount factor
Also for the
shared between both the principal and the agent, discounted future with discount factor.
The agent gets 1 no matter what is chosen.
No matter what is chosen, as long as something's chosen.
So that's the only incentive to choose.
Why? I don't understand why the principal is undiscounted it's theta, but it discounted.
Yeah. Okay, so in terms of final payoff, so to understand what are the ex post payoff, it depends on what was selected, when it was selected, and when did the principal do verification. So if for the agent it's easy, if you select a time t, the value from the perspective of time 0 is delta the t. For For the principal, it's slightly more complicated, not that much more complicated, it's delta to the t times theta, minus the discounted sum of whatever verification, or the discounted sum of the verification costs that are incurred. So the principal, that they could verify however, in any period, every period if they wanted to, and if they did, they would pay some kind of discounted cost of verification. If you never allocate, payouts are zero, unless if the principal has kind of already paid the verification costs, and they still pay those verification costs.
Delta, sorry. You pay C if you verify.
Yes.
But this seems to suggest that he always verifies.
So the assumption here is that they verified at T1 to Tk.
Yeah. Why would you assume that? Okay.
Just if they did. If they don't, then there's no C there. If they verify. So I'm going to make one mild assumption on chaos, which is just to make the problem interesting. I want the principal to prefer to allocate only to theta equals h. That's what, if I were to write the assumption in math, it would be that inequality. Economically, this is just the second best, not the first best. Okay, so
What's the expression on the left-hand side?
this is L,
Which is?
the value from selecting low quality.
Okay.
So then, yeah, it's, the payoff if you were to break out.
Can't you pick
There is no L missing in the right side,
No, it's, there isn't,
so I'm not sure I understand why this inequality
I think the L is
formula.
It's a little bit, so you get L if you, let me see if I can cut this. So if you select anything, you get L with probably 1 minus Q and H with probably Q. If you wait for high quality, then it's something involving delta and Q, right?
So what is
L
mean that
is
is
missing, yeah. The square L is missing.
I know this is like rearranged. I should write down the equation.
It's the wrong dimension.
I can do it on the whiteboard after the talk, but let's just, it doesn't really matter. All that matters is that the second best is not the first best.
But it can't be true because the dimensions are wrong. H is a dimension of money, whereas the other term is just a sheer number.
Let's kind of, I got this question before and I double checked that it was right and it's definitely right, but it's.
So just what the interpretation, I prefer H tomorrow over a random thing today.
Yeah, I mean, it might not be tomorrow, you might have to wait a longer time than tomorrow.
It's
So
probabilistic.
I'm not sure what do you mean, I'm not sure what the sentence means, so what do I prefer over what?
You would rather wait for high quality. If you could, if it was a decision problem, if the principal could see
It's yes,
the quality,
yes.
they would wait for high quality.
But it's probabilistic, there has to be an expectation.
Exactly.
Okay.
And that's why there's not an L, yeah.
So it's an expectation.
It's an expectation, yes.
Okay, when time is infinite, I prefer to wait until at some future point I will get H over taking immediately L.
Or H. If you stop immediately, it might also be H. You might get lucky, right? But yeah.
No, but you said I know the quality. So I observe now that the quality is L.
If you observe, yes. So if you observe the quality is L, okay. No. So it's a little. If you observe the quality is, it's a little bit different. Because if you were to decide to stop immediately, right? Then you get Q, you get H with probably Q, and L with probably 1 minus Q. If you saw that it was L, maybe you'd actually want to wait. So that's still possible.
So what I prefer is waiting until I get H over something random today.
Exactly. Which might be H. It might be H. It doesn't really matter whether this, in the break I'm happy to walk through the derivation of that inequality, but it's not important.
Okay, and explain the second best and first best. I always forget what those are.
I'll take the first best to be the case where the principal is the agent, in which case they seek quality. And in that case, the assumption is just saying that the principal would rather wait for high quality to arrive rather than just selecting anything today.
want to incentivize the agent to wait for consensus.
Even though the agent just gets one
But no matter what.
no matter what, but yeah, but that's exactly right. Okay, so a little bit about this. So we like in the paper we call this dynamic bias in the sense that the principal would rather only allocate to theta equals h. They would want to wait for quality. We allow, but don't necessarily require the agent to have static bias. Okay, and so this is kind of getting at what I was answering a little earlier. So, you know, it could be that actually selecting low quality is bad for the principal, right? It could be that they actually lose out, that if L is negative. If they saw low quality, they wouldn't want to allocate at all. And so we can let L kind of parameterize, in the case where L is negative, parameterize the degree of static bias between the principal and the agent. So I'll come back to that.
Is the first bullet the same as the last bullet in the previous one, or is that another assumption?
This is the same that's the same assumption. That's right.
Why is it called bias?
Well, it's just a conflict, right, between the principal and the agent, right? The principal wants to wait, the agent doesn't. It may or may not be the case that if it was a one period problem, that there would be a conflict. There might be no conflict with one period. There might be a conflict with one.
So it's biased from the perspective of the agent. The
I mean,
agent
yeah.
may be biased.
The agent may be biased.
Just to be sure, so the agent, we don't know yet what is the pair for the agent. We just know that he prefers.
I had this. The agent gets one from being allocated.
From being allocated, and here you say if it's L, sometimes he prefers not to be allocated.
So if it's L is the principal's pair, right? So
Yeah.
selecting low quality.
Yeah,
So if L is negative, the principal would rather select no project than a bad.
right, and the agent doesn't care about it,
Agent doesn't
he gets one.
Yeah.
Okay,
And why is it called agent bias?
I mean, if the principal is biased from the perspective of the agent is biased from the perspective of the principal. I mean, yeah,
Okay.
it's not.
If it's not-
I don't,
okay.
whose bias is what? I just want a dynamic static. That's kind of the thing that.
okay.
Okay, so we're going to allow for any arbitrary dynamic mechanism. Sounds impressive.
You did describe the interaction with the agent and the principal.
Yeah, that's what I'm doing now.
Okay.
So we allow for arbitrary dynamic mechanisms, but we're going to apply the revelation principle. It's very similar to what's in for Lippmann, except we add an induction step. I don't want to make too big a deal about this, except we do have the fact that this applies to some setting with limited commitment is maybe the epsilon novelty. But I want to kind of oversell this revelation principle argument. What does it mean? So given some history, which could include reports or verification outcomes, at any history, what the principal is going to do is specify as a function of the agent's report of quality a probability of verification, an allocation probability, which could depend on the agent's report as well as the outcome of verification. The outcome of verification can either be that it was high quality, low quality, or I didn't do verification. And the mechanism is also going to specify what to play in the future if no allocation is made. Okay? Now, for technical reasons, we're going to allow the principal to make use of a public randomization device. It's kind of, I don't really want to, it's just something that's going to ensure our value function is concave. So the standard trip.
And theta hat is the reported quality.
Exactly. Okay. Good. So, to start off, I want to think about what's going to happen in the case of two periods, because then everything you can kind of, it's just simple algebra, kind of rearranging everything. Okay. And in particular, I want to take two periods, and I also want to assume that the value from selecting low quality is 0. Okay. And that's going to be nice because now what the principal cares about is just the discounted probability of selecting high quality, and so that's the only thing we can think of. So the principal just wants to maximize the discounted probability of selecting high quality. Now, in the one period case, it's pretty immediate that the principal should just agree to accept anything. Right? Just, there's no reason, there's no real way of meaningfully eliciting information without verification. Okay? And even if there was, there's no real reason to try, because the worst thing that could happen is you get a low quality project, but that's zero, so it doesn't really matter.
Is that what they call hiring a secretary problem?
Similar, yeah, I should know that. Forgetting the exact difference of the secretary. Okay, but good, so yeah, so 2 periods, I wanna think about no verification. If you have 1 period, it's kind of obvious, you just give the project away. Question is, when you have 2 periods, is the best you can do to just give away the project right away? Is that the best thing, if you don't have verification? So when we are sort of studying this, I ask me how, what's the nicest proof? Give me a very nice proof that you can't do any better than just giving the project away right away. See how told me very gratefully that you couldn't do it because it's not true. So it is true if you think about the case where the selection rule has to be deterministic. So if the principal is restricted to using a deterministic mechanism, it's kind of clear that the agent is just gonna, all they only care about maximizing the probability of allocation, so they're just gonna select whichever message sequence just leads to the highest discounted probability of allocation, right?
And they would like to have it as earlier as they can.
Exactly.
Okay.
However, I want to think about the following mechanism. So in the first period, the agent is going to report quality, either high or low. And if the agent reports high quality, they get allocated with probability delta. Otherwise, they're never allocated. Okay? Whereas if the agent reports L, the project is going to be allocated with probability 1, but in the second period. Okay? So the idea is that the principal can, by randomizing, what the principal can do is screen using this indifference between delayed allocation on the one hand versus a lower overall probability of allocation on the other. Okay? So now, is that a good mechanism to use? I mean, they can do that. Should they do it? Well, let's just think. Well, if they were to allocate immediately, then the probability of selecting the high quality project is just the probability they get the high quality project in the first time, okay, which is with probability Q. If they use this other mechanism, then they get the high quality project in the first period is probably Q, so they only select it with probability delta. If they get the low quality project, then they get another chance. The value of that is worth delta. Okay, but they actually drop the high quality in the second period with probability Q.
You didn't specify the strategy of the agent.
So the agent is truthful, right? The agent, if the principal is using this mechanism, it's going to be truthful. Yeah.
Of course, that's the assumption.
Yeah. So I'm going to be restricting to incentive compatibility. I'll be assuming incentive compatibility. I mean, I need to show that it is incentive compatible, but this is incentive compatible.
This is what? This is what?
This is incentive compatible. Truth telling is incentive compatible.
Yeah, because he doesn't care.
Yeah. Because they get, the payoff is delta if they say high quality, it's delta if they say low quality. Okay. And so if you rearrange this, you can see that this is a better mechanism to use in immediate allocation whenever delta times 2 minus q is greater than 1. So what's the intuition? So the principal is going to have to withhold some high quality project if they want to do better. They're going to have to, there's no way around it, they have to sometimes lose out on the high quality if they want to screen the agent. However, the loss that you incur when doing that is relatively low when delta is higher. Okay? And if Q is low, then the probability that you lose out on a H quality project is also low. Okay? So the observation here is that the mere presence of dynamics provides scope for screening. Okay, the fact that you just have a second period or you have another period, that in itself allows the principal to screen. Okay? Now, as I alluded to, that's not really our, we're not the first ones to point this out. It's not really our contribution. Our contribution is to think about what happens when we use verification. And the idea is that what verification does is it lets the principal dispense with this randomization to a certain extent. So I want to think about an allocation rule where instead the if the agent reports where the high quality is allocated with probability 1, okay, but if I detect a lie, I can withhold the project forever. Okay, so I want to think about an alternative where we have verification, where I can perform verification and then withhold this project if I find out that you are lying.
When the agent reports age.
Yeah.
The principal determines whether that's a lie or truth, and then
if it's truth, they allocate. If it's a lie, they withhold forever. The question is, what does the verification probably need to be for that to be incentive compatible?
Do you check only high reports or do you check also low reports?
So you're not going to need to check any low reports are kind of not.
Yeah.
You know,
That's really something.
that's exactly something. Yeah. So the question is, what's the probability that the principal needs to verify a report of H in order to make sure the agent is being truthful? Well, if you denote that probability by X, you know, if the agent since the agent is getting allocated in the second period anyways, it's clear that you just need 1 minus X to be less than or equal to delta, right? 1 minus X is what the agent gets from lying, right? Because they get away with a lie with probability 1 minus X. Delta is what they get if they tell the truth, and so we need the probability their payoff when they tell the truth to be larger than what they would get if they lie. And so since verification is costly, the principal wants X to be as small as possible. So what does that mean? That means that X has to be 1 minus delta. So if the type is high, the principal has to incur this verification cost. That verification cost is C times 1 minus delta, right? Because they verify with probably 1 minus delta. If they verify, they pay this cost to C. However, the benefit is that they get this additional H times 1 minus delta by using this verification, right? Because now they don't have to label the project, they verify instead. Okay, and so you can see that whenever C is less than H, it's just better to use the verification rather than the screening methods, this randomization method. Okay, and so there's the question, what does high cost mean that for things? Okay, so whenever C is less than H, it's you verify with the intermediate probability.
L
In the first
is
period.
0 in this example?
L is 0 version. Yeah, so it's not obvious that that's also the general condition, even for negative positive L. We can talk about that. Okay, so the point is that with verification, the selection rule is deterministic, assuming that C is less than H, and it's optimal if the verification cost is worth it to implement these additional H projects. So key takeaways. So first of all, verification is useful here due to the increased efficiency over randomization. Now, if I had negative L, a difference that would emerge is that verification may also be part of the single period outcome. So there's no inherent use of verification when L is 0. But when L is negative, that's not true anymore, and that observation might actually flip the dynamics that we get. So that's something that's coming in a little bit. Another observation is that the higher delta, the lower the verification needs to be. The idea is that since the agent's getting the project anyways, if they're getting it tomorrow anyways, and tomorrow if delta is very close to 1, then they don't need to verify with very high probability to withhold it is very costly because they were going to get almost 1 from waiting 1 period. That really drives all of you into a strict farming results. Actually, the idea that once you get this, if you're going to get the project very soon, then you don't really need to worry about them lying as much. If you're going to have to wait longer, if it's smaller than you do.
So the agent has very low incentive to lie. That's it?
If delta is high, they have very low incentive to lie. That's it. Okay, so some misleading aspects. So first, the probability of verification here does not depend on C. Generally, with a finite horizon, as what will be true is that the verification path depends on the time at which the agent expects allocation. But one thing I'll flag is that C will influence the horizon. So there will be some dependence of the verification probability on the cost, but it will be through this channel which C will influence the horizon in this channel. And the second is that in this example, we have no values of verification if C is greater than or equal to H, and that holds for all delta. But one of our messages is actually that verification will always have value, so there's always benefits to verification, provided there's a long enough horizon and kind of enough patience. So we'll talk a little bit about what that is.
What do you mean that C generally influences the horizon?
So if you take C equals 0, for instance, then the principal would wait, then in that case, they would just wait forever, right? So there would be kind of no length. You'd be going for an unbounded length of time. When C is not 0, you will have a deadline at which point allocation will occur. So you can kind of see that depending on what C is, you might actually you might make more selections depending on.
So the example is misleading because T is finite?
Just T is 2, yeah.
But what if T is large but finite?
So we'll talk about that case. In that case, it depends on whether the finite horizon is binding or not. And if not, it'll depend, the path will depend. If it is binding, then the path will depend on what that is.
Does delta enter into that at all?
Does delta enter
Into that calculation you said?
yes, it will.
And here L is assumed to be 0.
Yeah, but in the general case, it won't be. That's another thing that's slightly misleading. In general, we'll have to think about how bad is it to select a bad value. Okay, so here's the general analysis. So we're going to do this kind of standard technique of formulating the principal problem recursively. Particularly, we're going to use the promise utility of the agent as a state variable. So the principal is going to have to choose a probability of verification, which will denote x of theta hat. Okay, that's the probability that you verify a report of type theta hat. If you report theta hat, then there's two possibilities. Either there is verification or there's no verification. If there's no verification, the principal will select an allocation probability, P, which we'll call P hat of theta hat, as well as a utility promise, which will denote U hat of theta hat. Okay? If there is verification,
What is the utility promise?
that is the, so that's kind of coming from this recursive formulation. There will be some mechanism that delivers. We won't a priori know what that mechanism is, but we'll compute it. We'll find out, we'll solve this problem for every utility promise, and then the utility promise will be the one that.
The utility promise is the same in all periods?
Well, we're formulating it recursively, so there's only going to be one period that we think about. But we're going to have this condition that the agent has to get this.
But what if the agent's strategy is not stationary?
That shouldn't matter. I mean, we're restricting to incentive compatible, so the agent is going to be telling the truth on path. Okay. So just to follow things, hats are no verification outcomes. Stars are verification outcomes. Okay, so P star, I mean, that's what happens after verification, and U star, and so on. So one thing I want to point out is that the principal can always just never allocate. That gives the agent 0. They can always just allocate immediately. That gives the agent 1. They can randomize between those. So it's immediate that any utility promise between 0 and 1 inclusive can be made to the agent. And nothing outside of that can be made to the agent either, as we want to track. Right? Now,
Why are the two utility promises different?
in what do you mean?
The one with the star, the one with the...
So it's just if there's no verification, there has to be a utility promise. If there is verification, there has to be a utility promise.
But why do they differ? They both refer to...
Well, generally they will differ, right? I mean, they're
It
different.
depends on theta hat and theta.
Exactly.
Already it's different.
Yeah, it's already different. Yeah, that's right. So, okay. So all of this in the background, we have this very nice Bellman equation. No, it's not.
And you say it's between 0 and 1. Utility promises?
Yeah.
Irrespective of
Yeah, because the agent doesn't care about it. It's the utility promise. What the principal should do is not obvious.
This is the utility promise for who?
For the agent.
For the agent.
Yeah, so maybe I should have been a little clearer about the technique. So the technique is,
At least
we follow, we say, let's think about how can we give the agent some utility level U. We're gonna solve that problem. And when we solve that problem, one of the variables will be what utility do we give them in the future. Right?
But the agent gets one no matter what.
Exactly.
So,
Well, if they're allocated, right? But
exactly, so where is extra utility? I don't understand.
so, right, so if there's an allocation, so if the agent, okay, so the agent is offered a mechanism today, and they get some utility level. Maybe it's 0, maybe it's 1, maybe it's a half, right?
From the mechanism itself?
Yeah, that's right. That's their expected utility from there. Now, that means there's some decision rule today, and there's something in the future, right? So today we'll specify something for the agent, and then tomorrow they'll get something else. And today's mechanism, like overall they should get U, okay, but then tomorrow they might get some other utility. Maybe they'll, in fact, if they're telling you, what we'll see is that they tell the truth, they should be rewarded, so they should get about that. So that's what's happening.
I guess it doesn't matter, but the agent can say something randomized, like with
Yeah.
probability.
They
But it
won't-
doesn't matter, right?
Where revelation principle holds, so they won't.
Because of the.
Okay, so here's the kind of immediate simplifications we make. So first of all, I think these are all pretty straightforward. If the agent was verified to lie, just don't punish them as much as you can. So in that case, the continuation utility should be 0. So the agent's continuation utility following a verified lie is 0. If the agent has has reported the high quality project, and either there was no verification or they were verified to tell the truth, in that case their continuation utility should be 0. Why 0? Because, I mean, you're waiting for high quality, right? That's what you're waiting to do, to select. And, if you got it, then you should front load everything as much as possible. Once you get high quality, you want to front load all of the agent's utility. So either they're getting allocated probably 1, in which case it doesn't matter what their continuation promise is, or they're not getting allocated in probability 1, in which case if you were incentivizing them by giving them some additional utility promises, you should just bring those forward and increase. You should just bring it forward, allocate with higher probability today, and not leave that in. Okay, so
I might refuse, I might not verify and refuse, but in that case, the promise should be 0.
So still be 0. Yeah, so you can see that from this screening we already talked about the screening. This needs to screen the agent, right? That's kind of an example where they tell me the high quality and I don't allocate. Okay, so if either if you verify high quality, just always allocate, there's no conflict anymore, you see what it is, right? And if the agent announced that they were low quality, pay off 0. Don't verify, no need to verify low quality. That's the thing that's hard for them to admit. If they told you it's low quality, there's no need to change it. Okay, and the last observation is kind of the standard one that the high type's IC constraint does not bind at the optimum, so we're not going to think about the high type pretending to be the low type. That's going to hold for free. Okay. So now we have a nicer Bellman equation. I'm not so embarrassed to show this on the slides. We have the value. So if the agent is promised U, then the principal will have something if the quality is high, if something if the quality is low. If the quality is high, then you verify with probability XH, and if you verify it, then you get H. You pay the verification cost with the verification probability, and otherwise you depends on the extent whether the probability you allocate to the high type without verification. If the quality is low, then you won't verify, but you'll allocate with some probability. If you don't allocate, you have some continuation.
What is U?
U is the utility promise of the agent.
So you maximize something, but there's no u on the right hand side.
So there's a u in this constraint. So u is what the agent, the meaning of u is that's what the agent has to be given by the mechanism. And it's just something if they have high quality, it's something if they have low quality.
I don't get that. So you maximize the expression on the right hand side of 5, subject to u being something?
Subject to u being this is saying the agent is promised u. U has to be what they're getting. It has to be the meaning of the promises. It's what the agent's utility is. What is the agent's utility? They get q if verification occurs, or it doesn't occur and they're allocated anyways. With 1 minus q, they get payoff 1 if they're allocated anyways. Otherwise, they have some continuation payoff.
I see.
Okay, so this is a little nicer, but there's still some kind of, it's not immediate to analyze this, and the reason is that there's some nonlinear interaction between these different choice variables, right? We have both an interaction between the verification probability for the high type and the allocation probability for the high type, as well as the allocation probability for the low type and the continuation value for the low type. Okay, so for this first nonlinearity between the allocation probability and the verification probability of the high type, we use a change variables. We define this y to be 1 minus xh times p hat h. And if you make this substitution, then you can rewrite promise keeping in this very nice way that it's just that it's y is equal to u minus q xh. Where does this come from? So remember that, and this is very important for intuition, that the agent is getting 1 whenever verification occurs. So the agent really likes verification, because verification ensures that they're getting 1. Y is everything else I have to be promised. Okay, so if the verification probability is, and in particular, this kind of doesn't really depend on, this is just, 1 minus xh p hat h, that's the low, y is also what the low type is getting, right? In equilibrium. That's kind of the definition of the IC constraint, right? Whereby the observation of the IC constraint has to be binary. Okay, so the agent gets y in either way, but the high type gets an extra xh on top of y. Okay? So it's just a kind of simple substitution. Okay, and so for the second nonlinearity, this is kind of the inverse of what I said for the utility promises for the high types are 0. For this other nonlinearity, we show that, we argue that you only kind of will set this allocation probability to the low type to be positive if you've run out of utility promises. It's only when you run out of these utility promises that you start allocating to the low type. Okay? The idea is that if you have the low type, you don't want to select, you'd like to wait, you want to move it as much, and so you should not allocate with any probability higher than it needs to be. Yeah.
You did mention commitment when you started.
Yeah.
Commitment means promise keeping or unrelated?
It's related. It kind of means, it's not all of, yes, sure. That's one thing it means. It means that the principle sets off to what the mechanism is at the start.
And it's not a game.
And it's not a game. At that point, it's not a game. So I don't need to think about would the principle want to follow through on this mechanism.
You can punish without any.
Exactly.
Wow.
When we relax commitment, the reason I said kind of is that we still use these same tricks. We just have to think about what is this utility promise. So it would still be something. So really, commitment means the promise utility is between 0 and 1. That's really what it means. With relaxed commitment, it's between something and something. Okay. So this is everything we need, and so now what we do is we introduce this tracing procedure to trace out the boundary of the value function. So what we do is we know what the value function is when u is equal to 1, and what we do is we calculate the derivative as we kind of change u, decrease u from 1. Okay, so we kind of trace out what this value function is, and then we kind of optimize it. So we set the initial utility promise to be whatever maximizes it up, whatever is the utility promise of the maximum value function. And what we show is that the solution is characterized by this three-region form, where in this first region, the agent gets, in this first region, this verification probability is set to be 0. In the last region, the verification xh plus y is equal to 1. Okay, and in this middle region, we know that the slope of the value function is h minus c. In this middle region. Okay, so I want to talk about the middle region first. I want to think about why does that happen. So this is, remember, this is the value function. This is based on all the simplifications and the relabeling. This is the value function that we have. And the constraints are that this xh has to be greater than or equal to 0, y has to be greater than or equal to 0, and the sum of xh and y has to be less than or equal to 1. Okay, so that's kind of the relabeling of the constraints with these changes in variables. And what you'll notice here is that this u is linear in y and xh, okay? And this maximum is linear in xh, in particular, okay? And what we show is that if you were to, at any point where xh is interior, you know, using kind of envelope theorem, chain rule kind of logic, we can just implicitly calculate that the slope of the value function is h minus c. Right? You can see that, you know, the change in u with xh, if I'm changing u by changing xh, u changes by q per unit of xh, and the maximum changes by q times h minus c per unit of xh. So q times h minus c divided by q is just h minus c. Okay, so the point is that if you're changing u by changing xh, that's what the slope of the value function has to be. Okay? Now the value function is concave, right? Because public randomization. So then, sorry?
Why is it concave?
Because we have a public randomization means that if the principal is getting some value at one utility level and another value at another utility, they can just randomize between those two utility promises, and they get the convex combination of those two. So they have to be doing at least as well as that. Okay, so that means that there's going to be some region where that is the slope of the value function, and to the right of it, the slope will be smaller. To the left of it, the slope will be larger. Okay. So now that's everything we need, and so what we show is that, okay, so either we have the slope is h minus c, or we have some boundary condition, right? Or, so either h minus c is the slope, or the slope is less than that, in which case xh should be as high as possible. You should max out xh as much as you can. Or it's going to be smaller than that, in which case you shouldn't be adjusting xh. You should make that as low as possible. Right? Okay, and so that's going to let us do all these substitutions and then make the tracing kind of very simple. Okay, so this is kind of what it looks like. So when you have u is sufficiently close to 1, when we substitute, we set in order to, we'll be adjusting p hat, right, in order to meet our promised utility, right? But we'll be adjusting, y, okay? And if you just stare at the value function, you see that it's linear, that it's something that's linear in y. So if you adjust u is kind of 1-to-1 with y once we make the substitution, and p hat l is 1-to-1 with y, and everything's linear, and so we can use that to kind of calculate the slope, right? So this is valid. This is kind of the description of the Bellman equation, or the value function, provided I would set u hat l equal to 1, provided that you've run out of continuation utility. If you were adjusting this at some point, p hat l will be 0, and that will generate a kink in the value function. Okay? So once p hat l is 0, you get a kink in the value function. Okay, but we just kind of continue this procedure. Now we get a slightly different value function, but it's still kind of linear in this region because we know that the utility promises are going to move us into this next region at every time. And eventually we get this one. We'll keep on going. Okay, so how much time do I have left? Like
20 minutes.
20 minutes. Oh, okay.
Can you go back for
Yes, okay. I'm doing
So
much better
the
at
agent
that.
utility is a function, the variable that the principal changes is P, the probability of checking. What is the
Sorry,
The agent utility is a function of what?
so the agent's utility,
It's a function of the mechanism.
it's a function of the mechanism.
But is there one parameter in this mechanism that we can think of it as the,
So what I want you to think about is why. Why is the thing that we're varying?
why is what exactly? Why?
So why is it's 1 minus xhp hat h? That's not the most intuitive variable. It's a little bit hard to see why that's the thing. But what it really is what the load type is guaranteed. Right, so it's what the load type is getting.
Oh.
So you could think of it that way.
The low type is the one who in the first period is low, or what?
Is in that period, it's the type
The
that's
specific period is
Exactly.
low. The continuation
exactly.
of a period is low. Okay.
So they drew low in that period, they have some utility.
So why is the function of P hat or P hat
They
and
had, it's a change, we did a change of variables, right, that was here. It's something that comes out of the math, and I have this intuition for what exactly is going on. But it's not a variable that you would have thought to write down.
so the function that connects between the agent utility and the principal utility depends on two factors: how much the cost of searching for the quality by the principal, and the change of behavior of the agent, right? Or the agent always says the truth, no matter what.
The
In
agent
all
will
this-
always tell the truth.
That's the truth.
Um,
So why it changes? Because of the. Can you go to the graph? So what happens there? Why it's when the principal changes the frequency of checking the
Yeah.
quality, the agent utility changes, and also the principal utility changes. Because of what? Only because it is checking more time, the
It's-
cost of checking.
There's a lot of subtleties here, so I would hesitate to
No,
say
it's
there's-
only this. There is no other.
Well,
Because it takes more time to take the project, maybe.
I mean,
Two factors, that's
Yeah.
all, no?
well, I mean,
What changes the principal utility? This is my question.
okay, so,
Only the time, because the agent all the time says the truth, so
yeah,
it's only the timing of taking the project
yeah,
and the number of times that it checks.
and the probability of checking. What is the probability?
The probability of checking is always, no matter what is the mechanism, always, if I understand correctly, always it checks only once, right?
Yeah, that one, yes,
Right?
yeah,
Once exactly, not less, not more.
exactly.
So it's only about timing. So when you show the graph, it means that the utility is lower only because it takes more time to get to the project, to take the project, right?
So that ends up being what happens, but you could have arbitrary mechanisms, right? You could have kind of a lot of different things happening, and it's only endogenously the case that it ends up
No, it's
being
not
that.
only the optimal mechanism, this graph, if you show.
This is only this is the optimum, this is.
Can you show the whole graph?
So that's
So this is the graph of the optimal mechanism, right?
under the yes.
So what makes difference in the level of the connection between the utilities? It's only the timing of taking the project.
No, okay, so timing is part of it, but remember, you're only verifying kind of in this region. So there's a region of the utility space where there's no verification.
Right.
There's a region where there is verification,
With probability,
with some probability.
yes.
And then there's this intermediate region. It's a little bit tricky to think about what that case is, and I'm happy to talk about it. It's actually, it's a little bit, it's something. But that's right, because there's these different mechanisms that the principal might be using, and so in this case, in this kind of right region, they're using verification. That's good for the agent, right, because they get allocated with probability 1 whenever they're high quality. But there's a left region where they're, in this region over here, they're not using verification, and they're instead randomizing the allocation.
Yeah, but what I wanted to say is that no matter which exact mechanism they pick, they all checks just once.
Yes.
So it's only about the timing,
So the
right?
reason I'm pushing back about what you're saying is that there's a time, yes, there's going to be a time at which there is an allocation. That's part of it. But the agent is doing better when there's verification. And that also is very important. And it might be that, and how long there's a verification phase is something that's endogenous. So it's not just the length of time, it's also whether the principal using verification is down there as well.
Right.
And it's through this kind of tracing that we can see what mechanism is the principal going to use.
Okay, that's the last point. So just to be sure, so in the mechanism, the principal may take the project without checking.
Yes.
Okay. So this is the point.
Yeah,
Okay.
yeah. Okay, so with all of this, I can tell you what the mechanism is because we've traced out the value function. Okay, and so we know that it's kind of linear, it's piecewise linear. Okay, and so that means that there's going to be some kink. Each time the derivative changes, there's a kink. So we just start off the mechanism at one of the kinks. And we know that because of the way the utility promises evolve, you jump from kink to kink. If you start off at a kink, you jump to another kink, and then so on and so forth. The final kink is not really a kink, it's u equals 1, and then allocation occurs. Okay. And so just by unraveling this process, we can describe the actual mechanism. And here's what it is. So it turns out that it lasts for some length of time. That's the length of time. And the way it works is that there's allocation following period reports of H for the first t star minus 1 rounds. Following any report of high quality, there's verification with an intermediate probability. This is what the probability is. This is set so that the low type is going to be indifferent between truth telling and lying. I should have emphasized this is for the case of low costs, right? Because with low costs, what we see in less than H, this kind of region where you stop using verification, that happens in a region where the value function is positive, or has a positive slope. So you never get there. So that's why you always will verify. You'll only use this verification mechanism and see this. You won't use something else. Okay?
You say it lasts T star means that it has to end by T star? That's not the
It means
expected time.
It means that any project is chosen at time T star. The expected time will be something less than that, but if you tried T star times and you haven't selected anything, you take anything at time T star.
The probability in 2 is decreasing.
Yes, that's not obvious, but you know, if you kind of work it out for T star equals 1 and 2, or if you set T star minus I to be 1 and 2, it's kind of clear. So if T star if T star minus I is 1, then it's just 1 minus delta. If it's 2, then it's 1 minus delta times this, which is greater than delta, and so on and so forth. But I guess the intuition here is just that this is, it's set so that the low type is indifferent, and the further away from the deadline you are, the more the agent has to wait, so the higher the verification probability has to be. So that's kind of the simple intuition for why, which is kind of related to what I was saying earlier. Okay, so very good. So this is set so that the low type binds, and given that punishment leads to no allocation. This uses the fact that the agent is eventually allocated, which relies upon either having no static bias, so L greater than or equal to 0, or an infinite horizon. So with an infinite horizon, you might wait for a long time, or you'll always eventually be allocated. What we show is that when
probability of verification is decreasing in cost,
over time.
but there's no time there.
T star minus I.
Minus I also.
Yeah.
Is,
So in period 0, it's T star.
okay.
In period 1 is T star minus 1. And, good. So if we decreasing skepticism, that's kind of our headline result. But the idea, a lot of what drives it is that you kind of eventually allocate. So one thing we show is that if you had a lot of static bias, so L is very negative, and the horizon is not too long, so it's a finite horizon, in that case you actually might have increasing skepticism. So you could get the opposite result. And we kind of identify exactly what that amount of time is, it's that. And the idea here is that if L is very negative and you don't have enough chances to draw high quality, the principal doesn't really want to just allocate anything at the end. That's not such a good idea, because maybe you get lucky, you might, if T is very small, there's a good chance you end up with low quality. And if L is very negative, then that's really bad. So the idea is that if you have a lot of static bias and the horizon is short, in that case, you actually want to, you'd like to end the mechanism with verifying. Right? You don't just want to give it away, you want to ask, is this high quality or not? So now the product process for the agent is, okay, you start off this sampling, you may have a lot of chances to draw high quality. So maybe you draw low quality today, you're not so worried about it because you'll have another chance to draw, maybe tomorrow you draw high quality and then you'll get allocated anyways. The issue is, what happens if you get to the end and you haven't drawn high quality? Now there's a real chance you don't get anything at all. So the point is that the closer you get to that if you have a lot of static bias and a short horizon, now over time it becomes less likely that the agent gets allocated. And that means that you actually have to increase the verification probability. Okay?
Very non-stationary.
Very non-stationary, exactly. That's a really, that's very much a big thing driving this. Absolutely.
What do you mean by static bias? You said he has dynamic bias.
So we assume dynamic bias.
Mm-hmm.
We don't assume, we allow but don't require static bias.
What is static bias?
So how bad would the principal be? How bad off would the principal be if they selected a low quality function? If the agent only wants something selected, could be that the acquirer is going to burn everything down to the ground, and that's going to be really bad. They're going to find the board members and find shareholders and rob them.
There are examples.
Exactly, yeah.
So it must be monotonous, either increasing or decreasing skepticism.
Yes, it will always be one of the two. It will
Because I
always be
can
one.
imagine a situation in which it's if the principal will take the project anyway in the end and the horizon is very long,
Yeah,
I could think of a situation which in the beginning is not skeptical, but then increasing and then decreasing, but
yeah. So
I don't know if it happens in new models.
it's interesting. I don't think we have any extensions where it's not monotonic. I have ways of breaking this and making it less stark, but I think the single selection is probably doing a lot. I think if you have multiple selections, then maybe you could have something else, but I don't know what that's called. Okay, so good. So for the C greater than H case, in the 2-period model there was no benefit from verification here. There's no reason to use verification. Here, and you might have thought that's kind of true more generally, that okay, if C is greater than H, there's no benefit to verification. However, even when C is greater than H, you may want to verify, but you will always verify at the end. Okay? So what we show is that when C is greater than H, the optimal mechanism will be characterized by 2 phases. The first phase you do this screening via randomization, and then the second phase you verify. Okay? Now, technically the existence of this verification phase depends on the cost of not being too high, and in the paper we kind of calculate explicitly like how high can the cost be. Just trust me that it can be, it can be greater than H. Technically you can see that from what I just described, because if the slope of the value function is if H is less than C, then that means that in this region where you stop verifying, the slope is negative, so you have to keep going. I don't really like that. I mean, that's mathematically, that's completely fine. But I feels a little bit, I don't think it conveys the right intuition. So I have a little simpler, more first principles argument for backloading, and this is the last one I want to talk about.
So what's backloading?
The idea that the verification phase comes second.
Comes second.
So you always will start randomizing and then you'll verify. Okay, so I want to think about this let's think about some arbitrary mechanism where the principal is randomizing for the first t periods. Okay? I want to think about what if you switch to verification. Instead of verifying at time t, instead of randomizing at time t, you use verification. I want to think about that change. Okay? So to know what probability are you allocating? Well, it depends on what the continuation value of the agent is. So let's say that's delta times ut plus 1. Okay? So the idea is that if you were to switch to verification at time t, then that's going to increase the agent's utility by q times 1 minus delta of the ut plus 1. Because if you're verifying at time t instead, if you weren't using verification, then the agent is getting delta times ut plus 1, no matter what. If you are using verification, that's still what the agent is getting if you draw low quality, but now if they draw high quality, they get a payoff of 1. Now the payoff moves to 1 if they draw high quality. Okay? So, so that leads to an increase in the agent's utility then. That doesn't just help the agent in time t, it helps him in earlier periods as well. Okay, by less, but by something positive. Right? So delta to the t minus s. Okay? So is this a good idea? Is it good to switch to verification at time t? Well, there's an added cost if you do that. The cost depends on the probability that you have to, that you first draw high quality at time t, which is this. It also depends on the probability you're going to need to verify at time t, which is that. Okay, and what's the change in your actual payoff in that case? Well, you pay this cost c, although you get to allocate h all the time. Okay, so the difference is c minus h. Okay, so that's the cost. Now, what's the benefit? The benefit is in period before time t, you also get to allocate with higher probability. Right? So now, because the agent's getting this continuation bump, the principal gets to allocate with higher probability, not just at time t, but also in period before time t. Okay? And if you were to compare these two expressions, you see all the terms involving delta, that they all kind of cancel. Okay? And the point here is that the second term accumulates. Okay, because this is what the principal can allocate more in every period before time t. Right? The cost is only born at time t, but they have an increase in probability in all periods before that. Okay, so this overall benefit is just proportional to the sum of its discounted probabilities. Okay, and it turns out that if t gets large, this will always be higher. Okay? If you kind of have enough of these terms accumulating, then you should always use verification. So the benefit of verification, that will very much depend on, the benefit itself will depend on delta, right? Because it depends on when you're using this verification. The benefit over randomization is not dependent on delta, which is maybe a little surprising. Okay? And so what this shows is that if it's beneficial to verify at time t, then it's also beneficial to verify at all later times t. Okay? Again, if this is bigger than that for some t, then it's also going to be bigger if I increase t. This term will just be getting smaller, and this term will be getting larger if I increase it. Okay? But so the point here is that the reason we get backloading is because it's a reward to the agent. And the fact that if you reward the agent by using verification, that if you kind of do this later, it can relax the incentive constraints earlier. What's not at all obvious is that it can be kind of arbitrarily good, that is, even if it's kind of the benefit from high quality is 1 and the cost is 10 million, you still will verify, possibly in the very far future, but with positive probability if it doubles that. Okay. literature, so we're in the part of this literature on costly verification without transfers. This application of board oversight of CEOs actually kind of predates us a little bit, but there's also precedent for that application. I should flag that this paper by Kovacs, Kramer, and Plattner, looked at this stopping problem without verification, so we attribute this screening by randomization mechanisms to them. There are kind of observations about this backloading, the backloading phenomenon, and the kind of what happens with verification. There's also literature on kind of repeated allocation without transfers, so technically that's kind of related as well. Okay, so we have in the paper, we have a extension where we kind of take the probability of drawing high quality to be proportional to period length, which is kind of nice because that kind of lets us look at this continuous time limit, which is nice because I can calculate very explicitly what the past will be. So in the paper, this is kind of the first thing we show, and the talk is the last thing we show. So this is what we find is that the headline result for the verification dynamics is this graph here. Right, so the probability that you use verification will be decreasing over time until some terminal date at which you select anything. Okay, but there's subtleties. So first, you might have an increasing verification probability, so we'll talk about that. If there's kind of a lot of static bias on the finite horizon, you might also have this kind of two-phase mechanism where first you're kind of randomizing selection, and then you're using verification.
These are not infinite models, right? Not infinite horizon.
This C and A are infinite horizon.
So in A, for example, when the skepticism goes to 0, the principal doesn't check, so the agent immediately will say always.
So it's always incentive compatible. The idea here is that the verification probability is very low, but the agent doesn't need to wait that long to get allocated anyways. So you're always allocating at the end. Here you're allocating at the end. With increasing skepticism, you're not allocating at the end. That's kind of the difference. I mean, you allocate if you draw high quality, right?
So it's the same. If the horizon is still long enough, it doesn't matter whether it's infinite or not.
That's right. Okay, so the kind of insight that I want to leave you with is first that this verification is backloaded. The intuition here is that the agent is doing better when the verification is used. Because these benefits accumulate, you always want these to go later. And interestingly, the length of this randomization phase is independent of discounting, provided that you have a long enough horizon. If you don't have a long enough horizon, maybe you don't. If you're not verifying, then the randomization phase might depend on discounting. But once you start randomizing, if you vary the discount factor, the randomization phase will have this. Okay, insight 2 is that you might have increasing or decreasing verification dynamics. As we were discussing, with an infinite horizon, you always get decreasing. But you could get increasing skepticism as well. And the static, one reason I kind of like this kind of result is you might have had this intuition that from the static models that the better types the higher types are earlier. You're like, oh no, this is just a static model. Yes, I have these fancy dynamics, but you might have said, no, Jonathan, this is a static model because the better types are earlier. And we know from static models that if the agent is claiming to have something better, then you should verify with higher probability.
What do you mean by higher types?
So this is a little vague. So there's other models in this verification literature where let's say I have a continuous number of types and the type is equality to the principal, or something like that. And in that case, you might have thought, oh well, you should verify more if the type is higher in that sense. And I'm saying you might have thought, oh, there's an analogy because you could have thought, oh, high types are earlier. The earlier draws of high quality, that's a higher type.
But at the same time, the cost also is higher.
The cost.
If you take the analogy to say earlier is higher, the cost of checking is also to verify.
That's a good point. So maybe that's part of why we get this. I have to think a little bit about if that's what kind of drives this. But I wanna it depends. I mean, the fact that it depends on the static bias, I have to think that it's not so clear that it's just about the cost, right? So anyway, I want to kind of flag that this, whether it's kind of if the earlier is in fact the higher type, that should, the point is to say that I think this analogy is problematic, right? Because it's endogenous, whether the high type is earlier, because it depends on the horizon. Okay, so I think I'm a little